Hey everyone, in this video I wanted to go over an example problem for a two-way test for independence using a chi-square distribution. So in previous videos I've gone over examples where we are doing a chi-square distribution question in a one-way table. And in this case, when we have a two-way table, that means that while we're still collecting information on one sample and focusing on one population, we are collecting information on two variables and we're plotting both of them into a contingency table. So let's go over an example problem and go through the whole hypothesis test process so we can start looking at the differences. So in this example question, I have a county health department enrolled 300 smokers in a randomized experiment. 150 participants received a nicotine patch and met with a weekly support group, and the other 150 participants received the patch and did not attend the support group. At the end, 40 people in the support group quit, while the other group had 30 participants who quit. Is there enough evidence to suggest that being part of a support group does affect the ability of people to quit smoking? So, focusing on our test for independence, when we have two different variables that we're looking at and we plotted them here in a contingency table, our null hypothesis is going to be that being part of a support group does not affect one's ability to quit smoking. So in my null hypothesis, I'm assuming that these two factors or variables are independent and they do not affect the outcome of one another. My alternate hypothesis is that being part of a support group does affect one's ability to quit smoking, and that would make these dependent events. So assuming that we're using a chi-square test for independence distribution and that all of the cells, I need to make sure that my expected values all have counts of 5. We need to figure out how do we come up with the expected counts in this two-way table versus a one-way table. Now in previous one-way table questions, maybe we were comparing one sample with a population distribution and we were given what that population distribution is. In this case, because we're assuming that these two variables do not affect one another, I'm going to be creating the expected counts based on the distribution of the data in my table. So for example, right now we're assuming that being part of a support group does not affect one's ability to quit. So in order for me to create my expected counts, I'm going to say, well, if these two events were independent, then I would expect 70 out of 300 people to quit regardless if they were in the support group or not support group. So in order for me to calculate my expected counts, for these two cells in particular, I look at my total, which is 70 over 300, and then I take that fraction and I multiply it by the number of participants in each of the groups. So in this case, to find the expected count, which I'm going to write right here, I have to take 70 over 300 and I have to multiply that by 150. So I'll go ahead and get that out on my calculator. 70 divided by 300 times 150 is an expected count of 35. So for two-way tables, I tend to write my expected counts in parentheses, just like that, so I can kind of compare the differences. Now, in order for me to figure out this cell, I'll do the same exact thing, but notice because I have 150 in each of the groups, I also know this is going to be an expected count of 35. Okay, so for me to find the expected counts of these two cells, I can say, okay, well, again, assuming that being in a support group does not affect your ability to quit or not quit smoking, I can say that the distribution of people that did not quit is 230 out of 300. And then if I were to apply that same ratio to both of these groups, I'd say 230 out of 300 is almost 77%. And then times that by the 150 people in this group gives me an expected count of 115. And again, because these groups are the same, I also have 115 right here. Okay, so once we've calculated our expected counts, then we can go over the conditions to see, okay, can this be modeled using a chi-square distribution? And the main assumption was that yes, we have data that was independently collected and each of our expected counts have values that are greater than or equal to 5. So now let's go ahead and talk about the test statistic. The test statistic and p-value, that process is exactly the same for a one-way test. We're going to take the difference between our observed and expected. We're going to square that, and then we're going to divide that by the expected, and then we're just going to take the sum of all of those values, and that's going to be my test statistic. So Thankfully, with this problem, we have whole numbers. So in this case, my observed minus expected is going to be +5. So I'll go ahead and just write these individually. I have 5 squared, which is 25, divided by 150. In this one, I also have a difference. It's -5, but it will give me the same value. -5 squared over 150. Right here, I have a difference of -5 as well. -5 squared over, in this case, oh, I'm getting ahead of myself. So I'm supposed to take my observed minus my expected and divide by my expected. So in this case, I'm actually dividing by 35. And then for these ones, I'm dividing by 115. I should now have divided by 150. So that's because my expected counts are different per cell. Here we go. Divided by 150. And then here I have a +5 squared divided by 150. Okay, so I can see that these are going to be equal to 25/35, which is the same as 5/7. If I add 5/7 and 5/7 together, I'm going to have 10/7. If I add all these together, this is 25 over 115. I made the same mistake when I was writing it. That's okay. I'm sure everyone knows that I'm intentionally trying to write 115, even though that wasn't happening. 25 divided by 115 is about 5/23, something like that. So 5/23 plus 5/23 is 10/23. So if I add this all together, my test statistic is the sum of all of those individual components. I have 10 divided by 7 plus 10 divided by 23 gives me a test statistic of about 1.8634. Okay, so how do we talk about the degrees of freedom? In this case, because we have a two-way table, the formula we use to calculate the degrees of freedom is slightly different. So my degrees of freedom is equal to the product of the number of columns minus 1 times the number of rows minus 1. Number of columns minus 1 times the number of rows minus 1. So in this case, I have 2 rows, 2 columns. So -1 for each of them. I'm going to have 1 times 1 is equal to 1 is my degree of freedom. So at this point, I can go ahead and plug in my test statistic and my degrees of freedom into my chi-square distribution to get my p-value. So I have GeoGebra open over here. I'm going to plug in my degree of freedom. I'm going to make it a right-tailed test. And my test statistic is 1.8634. And this is going to give me a p-value of 0.1722. So the problem did not state what our significance level is, which means I'm going to assume that it was with a 5% level of significance. Because my p-value is greater than alpha, that means I do not have enough information to reject my null hypothesis. That means that I do not have enough evidence to support my claim that being part of a support group does affect one's ability to quit smoking. Okay, so I hope this was helpful in going over an example problem for a two-way test for independence using a chi-square distribution.